A mathematics professor was giving a tour of the university to some new students. When he got to the cafeteria, he said with a flourish, "And this is our binomial cafeteria." One of the students asked, "Is it called that because there are so many choices?" To which the professor replied, "No, it's because you should buy no meal here." Get it? Speaking of which, I got a bonus. I don't know if you can see it, but my t-shirt says, there are two types of people: those who can extrapolate conclusions from incomplete data. Get it? I don't know if you get it or not. Anyways, let's get back to our lesson. So what we're going to look at is the binomial model. We're going to start with an example. 30% of M&Ms are covered in speckles and mixed randomly with normal candies. You buy a very large bag and remove 4 candies one at a time looking for speckles. Does the probability that a candy is speckled change if you draw only a few M&Ms? Well, I mean, honestly, I don't know if it really matters if you draw from the whole bag or not, but definitely if we do a small percentage. But I'm going to say that actually when they manufactured it, that's where the 30% M&Ms were set. And before they filled the bag, every M&M that went in there had a 30% chance of being speckled. So the probability doesn't change for any of the individual M&Ms. Now, if we are doing things like, say, using a card deck or other stuff, when we're sampling without replacement, the probability stays the same or good enough if we take less than 10% of the population. Just an FYI there, and we'll revisit that. So don't worry. And you're probably going, where'd you get 10% from? There's a lot of math behind it. We don't have time today. All right. So you've seen these tree diagrams before, right? So we're interested in determining the probability that when drawing 4 candies that 2 are speckled. So that means I have 2 to the 4th branches, 16 branches, and I've gone through the trouble of drawing them all here and even putting them on your notes so you don't have to draw them. So the only way we can figure this out is with a tree diagram right now, all right? Let's first look at the probability that the first 2 candies are the only ones speckled. So what I would want to do is I'd have 0.3 the probability of speckled times probability of speckled times probability of not speckled times the probability of not speckled. And when I put that all in, I get 0.0441. By the way, I went ahead and put in all the speckled probabilities. Remember that on the bottom here, any of these that match up, pair, or if you have more branches, they all have to add up to 1. So this is automatically 0.7. So what's the probability the last 2 candies are the only ones speckled? Well, it's the same idea, right? I just do 0.7 times 0.7 times 0.3 times 0.3, and I get 0.0441. So 4% probability, 4.4%. Were these probabilities the same? Why or why not? Yes, they were, because all I did, it's the same number of speckled candies and the same number of unspeckled candies. And so all I changed was what order I did that. And order doesn't matter when we multiply. Remember the commutative property where you can switch things? Yes. So when the probability of success, P, and that's a little p, does not change from one trial to the next, in this case, P was the probability of getting a speckled M&M. And we only have 2 outcomes. In this case, we're getting either a speckled M&M or we're not getting a speckled M&M. We call these Bernoulli trials. So what is the probability of drawing 2 speckled M&Ms regardless of order? Note the number of successes, X is 2. The probability of each success, P, is 0.3. And the number of trials, N, is 4. All right. Well, what I could do, because I have my tree diagram here, is I could just go through and highlight all of them, right? Say everyone with 2 successes, and there are 6 outcomes. So I can just go 6 times 0.3 squared times 0.7 squared, which gives me 0.264. All right. Well, if we change a problem of 2, drawing 2 speckled candies, to drawing 2 out of 5, then I would have 2 to the 5th. I would have 32 branches. That's too much work for me to do. I don't want to have to draw a tree diagram every time I'm doing a binomial distribution. So is there a faster way to figure out how many paths lead to my specified number of successes? Well, the number passed that give the two speckled M&Ms is called the binomial coefficient. And we often see it in the form of Pascal's triangle. I know if I have any math nerds here, you've probably seen this before. And also when you studied in maybe algebra or pre-cal, when you did binomial expansions, these numbers might look kind of familiar, like x squared plus 2x plus 1, x cubed plus 3x squared plus 3x plus 1. So you've seen this before. Well, so what we can do is these actually give binomial coefficients, right? So for this one, I have the 6 because there are 4 things to choose from, and I have not 0, not 1, but 2 are speckled. That's how we get the 6 off of the triangle. So I could just say, all right, so I'll just look up my binomial coefficient for n and x, and then do p to the x, so that's probability of a speckled, times to the power of how many speckleds I have, and then the complement to the leftovers, whatever's left over, right? But here's the problem. Okay, well, that works pretty well up to 8, and I could even probably do 9 or 10, keep a little printout with me. But what if I had 20? So there are counting methods that can do this, so we don't need Pascal's triangle, although it's cool to see it. All right, so we're going to start looking at counting methods. Just a very brief overview, just so you get an idea where the binomial coefficient comes from. So let's just say we range the 4 letters in word, right? And so how many choices do we have for the first letter? We have W, O, R, and D, so it's 4. How many choices do we have for the second? 3. And then for the third, we're down to 2. And for the last one, we're down to 1. All right. So if I compare the product of these choices, so 4, 3, 2, and 1, with the number of branches on my tree, they match, all right? So basically when I'm doing tree diagrams, that tells me how many branches I'm going to have, which is why I knew if I had 5 M&Ms and I have 2 choices every time, it's 2 times 2 times 2 times 2 times 2, or 2 to the 5th, which is 32. This is called the fundamental counting principle. All right, and it says that we can find the number of ways to get the specified set of outcomes by just taking the product, oops, my products, that's going to say product in a second, of the number of ways of each individual outcome. So we're going to use this to figure out how to rearrange SMART without doing a tree. So there are 5 letters in SMART. So I have 5 choices for the first, 4 choices for the next one, 3 for the third one, 2, and then 1. So I multiply all those together, and believe it or not, there are 120 ways to rearrange that. All right, a factorial is a special product of the integer and all the positive integers before it. It is written as a number followed by an exclamation mark. So if I want to calculate 9 factorial, and I'll go ahead and show you how to do it here, all right? Then I just put in 9, right? Hit factorial, and voila, 362,880. All right, so there you go. And whoops, there we go. And there's my product that I was missing. Okay, so now let's do something a little different. Instead of using all of the letters, we're just going to use some of the letters. So let's say I have 15 different letters to choose from, and I want to pick 6 of them and see how many arrangements I can do. Well, I have 15 choices for the first, then 14, then 13, then 12, then 11, then 10. Multiply all those together, and I get 3,603,600. All right. So is there a way we could use factorials to write this product more quickly and use the calculator or the stacklet? Well, sure. If I did 15 factorial, right? Problem is I've got too many digits. Look, I've got all these and I don't want them. How can I get rid of digits in a multiplication problem? Now, some of you might say, oh, subtract. Because I'm multiplying. What's the opposite of multiplying? It's dividing, right? So all of those simplify out. So I only am left with the 15 times 14 times 13 times 12 times 11 times 10. All right. And so notice that this 9 is just 15, this number up here, 15 minus the 6. All right? So that gives this is called a permutation, and it represents the number of ways you can arrange n items with a total of r choices to make. So we can write out an expression for general. So n is like 15 in our example, and r is like 6. So we would say that one way to write it is NPR, and you can see the symbol there, equals n factorial over n minus r factorial. So I could just take, 15 factorial here, calculate the n factorial, and then I could do the 6 factorial here and calculate that and divide by both. But luckily, both calculators and the Statlet have a function where it calculates a permutation automatically. All you have to do is put in the n and the r. So there we put 15 for n, because that's the number of things we have to choose from. We're taking 6, and we're figuring out the number of different ways to arrange it. And you can see this matches our answer from before. Okay, so we just learned permutations. Maybe that will give us our binomial coefficient. So I'm going to put in n is 4 and x is 2. All right. And let's see how that works. So I'm putting 4 and I'm putting 2 and I'm calculating NPR. I got 12. Wait a second, but we want 6. Why aren't we getting the same number? Well, permutations is when order matters and we can tell a difference from one position to the next. But let's say I have the 2 speckled M&Ms in the first 2 positions. What I'm trying to say here is if I switch the M&Ms, they're still both 2 speckled in the first 2 positions. Those look the same to me. All right? So when we say we want 2 speckled out of 4 M&Ms, we don't care which speckled we get first. So the order of the actual things, the successes, doesn't really matter because they're all successes. All right? So let's take a look at an example. Maybe this will help clear it up for you. We've got Braden, Ellie, Michael, and Zach, and all of them are applying for 2 lifeguard positions at the YMCA. Well, how many different ways can they pick the lifeguards? I could actually do a tree diagram, but I'm actually going to use a listing method. It's good for you to see those 2. So I could do Braden and Ellie, Braden and Michael, Braden and Zach, or Ellie and Braden, Ellie and Michael, Ellie and Zach, or Michael and Braden, Michael and Ellie, Michael and Zach, or Zach and Braden, Zach and Ellie, and Zach and Michael. But the question is there really a difference between Braden and Ellie if I hire that way or that way? They don't, as far as they're concerned, those 2 lifeguard positions are the same, right? And they are. So we would say, no, there isn't any difference, okay? So what do I need to do? I need to cross off all the duplicates, all right? So I've overcounted how many ways to fill the positions because the order didn't matter. So if we use a permutation formula, you saw we got 12, right? So how could we fix that? We want 6 instead of 12. Well, let's see. If I had done 3 kiddos, Braden, Ellie, and Michael, how many different ways can I order Braden and Ellie and Michael? Let's see. I could do Braden, Ellie, and Michael, Braden, Michael, and Ellie, Ellie, Braden, and Michael, Ellie, Michael, and Braden, Michael, Braden, and Ellie, Michael, Ellie, and Braden. I could do 6 different ways, right? What's a faster way to do that? It's how many choices you have for the first times the second times the third. In this case, we only have 2, so it's how many you have for the first times the second. Well, that's just a factorial of the number of things we chose. So 2 factorial ways. Order didn't matter, so we have to undo those extra outcomes that we're getting, okay? So we just divide by the factorial of the number of things we picked. And when we do that, we get the right answer. Okay, so the types of problems where order doesn't matter, those counting problems are called combinations, all right? So how do we take that permutation formula and adjust it in general? So now I have the combination formula, and Cx is n factorial over n minus x factorial. That's like the permutation formula, but I divide by the number of ways I can arrange the x items. All right, so you can see, let's go ahead and calculate it. You put in, we're doing 4 and 2, and instead of doing permutation, click on combination, and voila, There we go. We have the number of ways to choose 4 things. Now, you're probably thinking, oh my gosh, Mrs. Overman, this is a lot to do, right? I'm doing all this. Well, here's why you're doing it. You're doing it so you can avoid writing a tree with 2 to the n branches, all right? Because it goes 2, 4, 2, 4, 8, 16, 32. It just doubles every time. If you have 10 things you're choosing from, that's 2 to the 10th or 1,024 branches. Way easier to figure out the binomial coefficient. All right, by the way, on your math chart, you're probably not going to see NCX. Instead, you're going to see that notation, N over X in parentheses. Please don't confuse it for a fraction. It is NCX. How many combinations when you have N things to choose from and you take X?